This is part 2 of lecture 1. In the actual lecture, we'll start this by playing a game, or as a quiz question, which face is real. So if you go on my website, and under week 1, under other materials, there's a link to which face is real. If you click on it, you will see two faces. One of them is real, the other one is computer generated. And you are asked to click on which one is real. I think both of them look real. I'll guess this one. Yes. So if you click on play again, you'll see another two, and they both look real again. So I will not guess it here, but we'll play this many times during the lecture, and we will see who can guess it correctly consistently. So, and anyways, the reason why I want to play this is I want to briefly introduce an algorithm called generative adversarial network. We will go into more details the week before the midterm, but I will briefly talk about what this is. So I think many of you may have heard this as deepfake. So the algorithm that is used to generate deepfakes is called generative adversarial network. The main idea is there are two parts. The first part is called the generative part, where the algorithm inputs a random noise, basically a random image, and outputs fake images. So it basically converts random noises into fake images. And the second part is called the discriminative part, which inputs the real and the fake images generated by the generative part, and the output is a label whether this is real or fake. So basically, the generative part is trying to create fake images that look real, and the discriminative part is trying to distinguish actual real photo and fake images. So if we have two things that are good like this, how are we going to make them better? The only way, of course, is to make them fight. So we will let these two parts compete. So while they're competing, the generative part will get better and better at outputting better and better looking fake images, and the discriminative part will get better at distinguishing real and fake images. So if we let them fight long enough, then the generative part will get really, really good at producing fake images that look real to try to trick the discriminative part to classify it incorrectly. So it will be really good, and at the end, after a long while, the generative part will be able to produce really good images like the one you saw in the game. So that's the basic idea, and we'll go into the details of both of the parts, and both of them are called supervised learning. We will start the first week. The first few weeks will be on the discriminative part, which is basically how to classify two classes of things, how to separate two classes of things. And the lectures closer to the midterm, we will start the generative part. Basically, we're going to generate new stuff. So basically, first half of the semester is on supervised learning. So let me introduce supervised learning with more examples, in particular here, this discriminative part of supervised learning. So other than the real and fake images example, the most typical example is images of cats and dogs. So I will start with this. So I guess many of you have seen the meme, this one here, where some people have no idea what AI is, thinking AI will destroy the world, while you will be doing this neural network actually in the first programming assignment, so you will see how you do. So it's actually very difficult to classify whether an image is a cat or a dog. So in the first programming homework, you'll be asked to classify handwritten digits. So handwritten digits, you'll be classifying whether it's a 0 or 1 or so on. So you can see the performance of the neural network that you will be creating. Anyways, let's get back. So let's actually get an image of a cat and a dog here, placed here, so we can compare them. So we want to use machine learning to try to classify cats and dogs for new images, but we need to be given existing images of cats and dogs. So that would be the data part. My pen is not working. Let me switch to another one. This. So at the beginning, we are given a bunch of images, and they are already labeled as cats and dogs. So the goal is to find a function that when we are given new images, we can still classify them correctly. So in order to do this, when we are given an image, it's hard to apply any function on image. So we need to convert the image to some numerical values, and we call those numerical values features. So basically, we want a vector x that can be input into a function, into a mathematical function, and output the label. So the x can be, for example, the height, the length or the width or whatever it's called, and the eye color, for example, of the object in the image, and we summarize them in a vector, say x, and we want to find a function. So the goal is to find this function that when it's applied on this vector, it can give you an output, and that output specify whether it's a cat or dog. So that would be our goal. So ideally, we would want something like height or width or something like that, but it's hard to get these information directly from the image actually. So if you're given an image like this, you don't even know where the dog is or where its eyes are. So it's hard to get these actual features. So what we'll do instead for programming homework 1, and also for many image-related tasks, is using pixel intensity as those x. So what I will draw a small image, and each grid is called a pixel, and each pixel has a color. So a color is specified as red, green, and blue, RGB, and we take the average of these three numbers. These numbers are numbers between either 0, 1 or 0 and 255, but in any case, we can convert the amount of red, green, and blue in a pixel to a number, and we average that number, and the average is called a pixel intensity. So we'll use this as the first component of x. So this is x1, say this is x2, x3, x4, x5, x6, and so on. And then we list them in a vector, and that vector is called x, and then we try to find a function that map x to a label. The label is either a cat or a dog. So if this diagram is not clear, let's actually open another image. This image is actually hard to know whether this is a cat or dog. I guess it's a deep fake, but in any case, I just want to show you what I mean by use the information about each pixel. So if you zoom in, you can actually get to see that the image is formed by a lot of pixels. Each pixel has a different color. So if you use the pencil, you can click on it. You will highlight, say, 2 pixels, and 1 pixel, and you can use different colors, for example. And you'll see that every pixel has a color, and that color has red, green, blue components, and the average will be called the intensity, and we'll use the intensity as our feature. So let's get back to here. That will be our first example. Next, let's move on to a more, say, typical example. More realistic example. Well, the cats and dogs are a realistic example as well. But, say, more useful example is the medical records example. So we are given data of the medical records of patients, and for example, the features would be some kind of scan images and blood tests and so on, and the output, the thing we want to classify, is whether they have some specific disease or not. So for example, here recently we have those COVID-19 coronavirus tests, and these are basically based on some test results, and we want to find a function that can given the test result, which we'll call x, we want to find a function that classify whether this patient has coronavirus or not. So this is the output y hat. So again, the goal is to find this. We're given some of this, and we want to find this function f so that we can classify new stuff. So for the so a similar example is if you have the age information, you have pre-existing condition information, you can try to classify the probability or whether a patient is likely to die or not. So that's just a similar example. And let's move on to the third example. So third example is similar to the face images that we saw at the beginning, the real of fake face images. And here we'll talk about the features. So some of the important features are, what are the edges in an image? What are the corners in an image? These things are defined properly in computer vision, so we will talk about those. So how to actually generate these things from an image. But the approach that we're going to use, which is called convolutional neural network, is bypassing this directly from the pixel information. We'll be able to directly label a face as a face or not a face. So a similar problem is if you have self-driving car data. So here the images are 2D, and if you have the self-driving car data, one single frame would be a 3D image, so you have the distance or depth information as well. If you include the movements, then it's basically 4D images or 4D videos. I don't know how to call these things, but it's just higher dimension, and in the data in each dimension is somehow related. So there are special methods to deal with these type of problems. As I mentioned before, they're called convolutional neural network. We will talk about them in like 2 or 3 weeks. And the next set of examples will be related to natural language. And the field is called natural language processing, NLP. And some of the simple tasks include labeling emails as spam or ham. So ham is a special word in machine learning that says it's not spam. So ham, not spam. So we are basically given emails. We want to kind of find features that are numerical. So some of the important ones are word count. We'll talk a lot more about it in closer to the midterm, and a number of things are capitalized and so on. So we will convert the emails not to just strings, but to numbers, and those numbers will be our feature vector. And again, we want to find a function that can be used to classify whether it's a spam or not a spam. So the special property of these things is when you have an email, when you have a comment, the sequence of words are formed in a sequence, so they are sequentially related. So if you look at the previous examples, you can see that x1, x2, x3, they may not be related somehow. So, but here we treat them as sequences. So f of x1, x2, x3, and so on. If you switch the order of the words, it means something different. So the order does matter. So again, there are special algorithm to deal with the sequential nature of the feature vector. And what we will do, again, near the midterm is called RNN, recurrent neural network. So here is just some examples of these. And other examples, for example, is you have movie reviews, you have restaurant reviews, you want to classify whether it's positive or negative, and you have financial transactions, which are sequential as well, and you extract some features and you want to figure out whether there's fraud or not. So these are basically all related to the natural language processing. And let's see, the next example is kind of repeated, and the handwritten digits, as I mentioned before, it will be your programming homework 1. You will be asked to classify digits, so you'll be classifying whether something is a 0 or 1, which is kind of easier than in general classifying letters, because you have 0 and O and capital O and so on, which they look similar. And there are also these things. Some people write delta and sigma the same way, so they are hard to distinguish as well. And also this is phi and psi, they look similar as well. So it's kind of hard for humans to distinguish different handwritten letters as well. So of course these tasks are harder for machines to do. So a similar example that is kind of hard for humans to do as well is voice recognition. So the features will be signal, just like the pixels. They are basically the original format of those either images or voice recordings. And for handwritten digits, we may want to convert them to strokes. And for similar idea is for voice recording, we may want to convert them into sound. So I will explain what these are later when we actually see them. And some example of stuff that are hard to classify is, say, recognize speech and recognize speech. They sound similar, so you do need to use context to figure out whether it's the first one or the second one. So basically, these tasks are hard for humans to do. And for some of the previous ones, like email spam and other things, and especially cats and dogs, they are very easy for humans to do. It's just there are lots of them. We don't want to spend time, so we want to automate them. So these are the ones that are actually harder for humans to do, and we also want to automate them. And there are even things that are even harder for humans to do. So, for example, if you get a painting, you want to classify the painting as art or garbage. It's kind of hard to decide. When I see a painting, I don't know if it's art or not. So I guess sometimes during the semester, we'll actually try this. I'll show you some painting and ask you whether it's art or garbage. But in any case, some of these are hard for humans to do. So it's even harder, for example, to ask an AI to paint something, to do some art, do something nice. It's kind of hard, because these are not well defined. For the same reason, when you are grading essays, it's hard to decide whether someone gets an A+ or an F. So the different TA will grade this thing differently. So it will be different to train an AI to do some tasks like this. But we'll talk about how to deal with these problems as well. So they are called unsupervised learning, but we will talk about this after the midterm. So before this, let's actually summarize what we were trying to do. So we were trying to, given a vector of numbers, we want to try to find a function that classifies that vector into one of the few discrete classes, and we call it y hat. So if x is two-dimensional, for example, only x1 and x2, then we can actually draw it. So x1 is here, x2 is here. So we are given some existing, say, cats and dog images. So for example, these are cat images, and these are dog images. And say x1 and x2 are feature 1 and feature 2. Let's say 1 is the height, and 2 is the, say, the eye color. It's kind of hard to define eye color as a number, but in any case, suppose we can. If we want to find a function, we just want to find a line that separates the classes. So sometimes we may have an x here, so sometimes this is not exactly a line, it can be a curve. But the goal is just to find this function represented by a line or a curve or something that can separate the two classes. So that would be our main goal of supervised learning. So as you will see, all the algorithms are trying to just do this. And now let's formalize the task of supervised learning. So we are given samples, and these are called features. So we usually use the letter M to denote the number of features. So for example, for the cats and dog images, 1, each pixel would be a feature, then m would be the number of pixels in a image. So note that all of the images need to be resized to have the same dimensions, so the m is the same for all the input samples. And n is usually used to denote the number of samples, so basically the number of images we have. And we are given the ones that are already labeled, so the number of images and the number of labels should be exactly the same. And given these things, as we saw here, we are going to try to find a function that can separate these two classes the best. So we're going to use these things to find the best f that can separate the two classes, or maybe more classes. So we want to find f hat on this x such that it's very close to the correct labels. And then the task is, when we get a new image, for example, we get a new image, we get the same features as the ones in the sample. We want to classify what this new image is, then we just apply the same function that we learned from the sample and apply it to the new image. And this function, since it's applying on the same features, it will give you a number, whether it's a cat or a dog, for example, and that would be our best guess. So that's the main process of supervised learning. So some people may introduce this slightly differently, so I will talk about it that way as well. So some people would separate the training set, separate the sample into two parts. One is called the training set, and the other is called validation set. So what they mean is the training set is actually used to find the function f hat, and the training set may be used to find multiple possible good functions. So we'll find this one, and we'll find this two, and so on. And we use the validation set. So we basically split the given sample that are already labeled into two parts. And this second part, validation part, is used to figure out which one of these is the best. So suppose we select this one, then we will use this one as our best guess. And when we see the test set, which is the new images, we will use the best one among the ones that we have. So in this lecture and the next few, I will not distinguish training set and validation set. So basically, when I say sample, it just means the training set. I will use all the sample points to train this best f hat, and we use this f hat on the test set to label new images. So I will go over these in the next part of the lecture.